Yeah, before I saw that Alexander had his hand raised, I don't know if you wanted to add something maybe to what David was saying.
It's fine. I'll just write an email.
Okay.
All right. Okay.
That's okay.
Yeah.
Okay, so well, thank you very much. Let me just share my screen. If the host can let me or enable me to share
Oh,
my
yes,
screen.
yes, yes. Sorry.
So very nice to meet you all. Some of you already know me. I see some familiar faces from the thread group. My name is Alejandro Calderon. I'm a PhD. I'm a researcher in the Global Earthquake Model Foundation, which you know as GEM. And the focus of my PhD and my research here at GEM, it's the topic of today. Basically, it's about assessing future earthquake risk. And so the presentation of today is I just gathered some slides from these past 8 years of experiences and research that we've been doing here, just to let you know what this topic is. It's a general presentation just to give you an overview of what it's been done regarding this topic by us, by other people, and as well so you get a general idea of it. And I'm leaving you here my email. So if there is any question that you get like later on during your research or in your future professional life, just feel free to contact me. I'm happy to help. But also, since we're few today here, feel free to ask any questions, interrupt me, raise your hand. It's always nice to make this as interactive as possible. So thank you very much again. And let me start talking about this. So assessing future earthquake risk. This is something that it has become quite fashionable nowadays. It's not uncommon to find project proposals, development proposals that are asking researchers to, study earthquake risk in a region, but at the same time, not just look at today's risk, but the risk that we are going to have in the future. So this is something that is becoming quite common, and you can find a lot of literature regarding this topic. And I would like to start can you see my screen? Yes, you can see my screen, right? I would just like to start showing you why this is important. So when I started doing my PhD around 2018, I was doing my PhD, and we were approximately 7.6 billion people on the planet. And in just 5 years, I'm just putting here some statistics of how much the world has changed in just 5 years. So, for example, if you take a look at how many more residents we have in the planet, it's almost 400 more million people. That is equivalent of adding the United States and Canada to the planet. How many more residential dwellings we have constructed? That is almost 100 million more residential dwellings. That is equivalent to adding a new Indonesia and a South Korea in just 5 years in the planet. And the same is happening when we think about buildings, new establishments, new industries, new residential buildings. That will be 100 million more buildings is equivalent to saying we have a new Brazil and a new Argentina on the planet. So you can start having a guess of how much pressure we're putting into the planet, and how that will translate into a possible increase in the economic losses that comes from disasters, from natural disasters or natural hazards, let's say. This is a plot that I think you've seen in the past. Basically, if you take a look at what GAR, or the Global Assessment Report, says, it says that we're currently at the peak of the number of disasters that it's being reported per year, and we expect 40% more disaster events, recorded between 2015 and the decade of 2030 than in the previous 4 decades. Now, there's some disagreement with this. Yeah, I've seen in some researchers saying that no, we are observing more disaster losses basically because we are better at registering them. Now we have recording stations, now we have the internet now, so we are better at reporting earthquake losses or hurricane losses or floods or droughts. And that's one point of view. I'm more on the point of view that this is actually accurate. If you think about it, like in 1900, we were like less than 2 billion people on Earth. Now we are more than 8 billion people on Earth. So if you assume that disasters or natural hazards occur with a constant rate, then our increased human presence on the planet for sure is going to translate into seeing it more disastrous events as we increase that presence in the planet. But also constant rate of events might be true of earthquakes, but due to climate change, right? This is not necessarily the case. We can expect a higher occurrence in droughts, in floods, in hurricanes, for example, typhoons, things like this. So I do believe that this trend is exactly what you see here, and it will most likely continue. So how are we as societies coping with this? And then to provide you some examples, I'm putting here countries from all around the world. So I'm giving you the example of Netherlands, Japan, Cuba, Bangladesh, and Australia. These are different countries with different levels of development. And but they are famous because we always see them in the news, but either being affected by droughts, by climate change, by strong earthquakes. So it's worth it to take a look at how they're dealing with this, how they're dealing with so many frequent hazard events. And if you take a look at the main strategy to reduce risk in these countries, it's always talking about minimizing the loss of life. In the countries that have a lot of resources like the Netherlands, building new infrastructure to safe protect people, new dams, and in countries where maybe resources are not so abundant like Cuba and Bangladesh, then it's about relocating the vulnerable people, relocating people from areas where we know that are prone to natural hazards and moving them to safer places and things like this. But the interesting thing is when you take a look at these main national strategies that these countries have in place, and you take a look at the time scale in which these strategies are supposed to be working on, they're never strategies for this year or for next year. They're always for the next decade, sometimes for the next 50 years. Sometimes, for example, in the case of Netherlands, due to climate change, they are already forecasting what the risk will be in 100 years. So my main question to you is, if we are scientists or researchers or of the earth, of natural hazards, of natural disasters, and we think that our models should be the main tool to support these strategies for mitigating risk, shouldn't our models also be time dependent? Shouldn't they be taking into account what's happening today in terms of risk, but also what it will look like tomorrow? And then, yeah, I think that the question should be, yes, we should start thinking about how to improve our models so they can be useful not just to understand the risk today, but to understand the risk tomorrow. And this is basically what today's lecture is. I would like to explain to you more or less how we can do this. And then but it's a little bit difficult, right? Like when you think about, and I think you've heard that risk is deconvolution, or it has three main components, right? It has an exposure component, it has a hazard component, and a vulnerability component. So we are in a condition of risk, or if we have, for example, a hazardous event, an earthquake, a hurricane, a flood, or a drought, and we have people and assets exposed to it, but also those assets are vulnerable to that hazardous event, right? So it means that if we want to take into account or to estimate future risk, it's not just enough to say, well, we have this many more people or this many more buildings, and then the risk is going to increase by that much. If we do that, then we're only taking into account one part of the problem. In reality, we need to think, okay, we're going to be more people or less people, we're going to have more assets or less assets in the future, and that's one part of the equation. But we also need to understand what will be the vulnerability in the future. So in the case of earthquakes and buildings, will we be building better structures? Will be having better seismic codes? Are we going to take that into account in our analysis? And in that way, then we are making a more realistic assessment of future risk. And in the case of earthquakes, for example, here the hazard I have grayed out, because in the case of earthquakes, we can understand that earthquakes are not like the rate of earthquakes that we will use in our models is not supposed to increase in the future. We can assume that we're going to have a constant rate of earthquakes. But this is not, again, this is not true for other natural hazards. It's not going to be true for floods or for droughts or for hurricanes as the climate changes. So if that is the case, then we have another component that we need to take into account in order to do robust models that can take this dynamic risk into account. So it is complex. So in order to understand, for example, what will be the increase in risk, earthquake risk in this case, by the year 2050, we need to take into account these two components. And then I would like to think, or I like to divide this problem into three main questions. That if we are able to answer these three main questions, that we are in a good, or we will be able to produce robust models. So these questions are addressing change. Basically, the first one is how many. So how many more people, how many more buildings, how many more industries, businesses we're going to have in the future. Where are they going to be located? The location is quite important for natural hazards because it means that we are going to associate that with the probability of having an earthquake or with the probability that we're in a flood zone or in a future flood zone. And how vulnerable, obviously, because we want to understand, associate intensity measure levels with losses. So those are the questions that we want to ask, but then we need to take a look at the drivers of that change. So how many more people are we going to have in the future? Well, the drivers of that will be the life expectancy, the death rates, the birth rates, the immigration in each country, immigration, the economic prospects of each country. Where are the assets going to be located? New housing, for example, that depends on land use, availability, affordability, the opportunities of that cities provide for housing, whether there is access to amenities in this area. Does this make it attractive for people to build there, to develop there? Or in other cases, maybe just abandon this area and move on to a new area. And then when we think about how vulnerable, the drivers will basically try to understand construction practices. For example, I've seen new codes being so strict that people cannot follow them. Like low income families prefer to keep building the same way we are building or we have been building because new construction regulations are just too strict. Or living standards. If the economy is doing well and we have the money to hire an engineer to build our house, then yes. But if not, then any mason will have to do. Government regulations and interventions. So all of these drivers are influencing these variables. And then when we think about how all of this has to end up in our models, right? In a risk model, we're going to have to end up with target parameters, basically how many more people are going to be in those models, how many more buildings are going to be in those models, what is the value of those buildings in those models, are those buildings going to be located in a high hazard zone or in a low hazard zone, and which fragility or vulnerability functions we're going to assign to those new buildings. So as you can see, like the level of complexity can increase, but if I like to dissect this in these three levels and then try to answer each one of these questions individually. So regarding if we start thinking about the exposure component and we think, well, how many, we're trying to answer this question. As I was telling you, we might be tempted to think, well, let's add just more people to our models and that's it. But we need to understand where are they. We also need to understand if more people translates into more buildings, right? So when I started doing my PhD, I was trying to find in the literature like a golden relationship that could do this, like maybe a paper says, if we have this much increase in population, then we can see that we're going to have this many more buildings in a specific country or in a given region. So I started collecting a lot of data and trying to come up with this relationship or to see if it already existed in literature, and it doesn't. And at the same time, I was trying to then come up with this relationship, but it's hard to make. As you can see, there is very low correlation if you take the observed change in population in all the countries around the world, and then you map that to the change in construction area, for example. It correlates, maybe not. I mean, it's not a good model. So it's actually quite challenging. There's definitely not this golden rule that would allow us to say, well, just these many more people translate into many more, I don't know, buildings, houses, gross domestic product. So it's challenging. I also try to, during other experiences, we try to say, well, maybe it's not just the change in population that you should look at. Maybe it's the economy what is driving the increase in the built environment. So, for example, in the case we were studying sometimes countries in Europe, Italy, France, Germany, Romania, and then we were trying to understand, well, maybe the change in the GDP, because these are advanced economies, is going to correlate well with how much more infrastructure they have built across the years. And again, it's okay, yeah, you can make the case, but it's difficult because some countries like Luxembourg have amazing economies, but they're small, they don't build that much. And some countries are big, like Romania, and the economy there is not as good as in Luxembourg, but they still build a lot of housing, a lot of new buildings, establishments. So it's difficult to come up with this golden relationship. It was hard to find this variable to variable association. And why? Well, let me give you here an example. Here I'm presenting you 3 different countries, again, from different parts of the world. The Dominican Republic is a small Caribbean country, around 10 million people. This is a country that by all metrics is a developing economy. It has an increase in population. In 10 years, it has added 1.5 million people. In 10 years, it has more than double its GDP. So what I want to see is if we can find a correlation between these increases, this level of development, and the new residential houses that they're building, for example. And then we can compare it to Serbia, for example. Serbia and Albania, these are 2 countries in the Balkans. The Balkans is a region where population is actually decreasing. And you might expect, well, then maybe this will correlate negatively with the amount of growth that they're going to have in the residential sector. So they have, for example, Serbia in 10 years has lost 8% of its population, Albania more or less 5%. And even though their economics are doing well, yeah, the demographic prospects are not so positive. So which one of these countries do you think would have or show the highest increase in the residential infrastructure? Well, it turns out that it's not easy to find that correlation. The Dominican Republic indeed has like a very good, in less than 10 years, they increased by more than a fifth or a quarter, let's say, its residential infrastructure. But the highest country between these 3 was Albania. So it's difficult to understand why Albania is building more houses if it's losing population. And I would guess that the conclusion here is just because the build environment is evolving in response to more complex factors than just adding more houses or the economy is doing great. Certainly those factors weight into the equation, but they're not the only ones. So it's a challenge. It's a challenging a problem to solve. So if our main goal is to come up with time-dependent risk models, how can we do this? Like how moving forward from this, how can we better or improve our models? So on the exposure side, I think what we need to do is start collecting additional data for drivers of urban growth, but at a global scale. And not just at a national scale, but at a subnational scale. Like let's try to understand these things, but with better granularity. And we have to also explore better ways to account for these drivers. There's not just this one variable to one variable relationship. It's just not good enough. So just to give you an idea of how this can be done through, well, now we're going to get a lot of information from for example, just this year, 82 countries are preparing to release new digital housing and population datasets. Some of them, for the first time, are going to have more than one census. In Africa, for example, in the Middle East. And for the first time, I think all this information can be paired with Earth observation datasets about how many more buildings we're building, how many more construction area we have, how many more volume of construction we have in the world. And I think improvements in this data availability, resolution, and global coverage, this basically can translate into better studying the evolution of the built environment. And just as before, trying to find relationships, but this time using more robust statistics and data science. So just to give you an example of how this can be done and how we're doing this, actually, I'll give you the example of Mexico City, okay? So instead of, I was telling you that we were studying changes at a national level, right? But what if we take a look with a higher granularity, right? So instead of seeing national changes, let's take a look at subnational changes. And instead of taking a look on just one variable, let's take a look at many variables. So if we take 3 points in time for Mexico City and we study how much the number of dwellings changed in that time, the number of households changed in that time, what is the average occupancy of a dwelling in that time? How many people were working in agriculture at that time? How many people were working in services? How many people in industry? And then not just demographic variables, also urbanization variables. So how much was the total constructed area in these 3 points in time? How much of that area was urban? How much was rural? How much of that area was residential? How much was not residential? And then also geographic variables, because these changes are not happening in the void, right? So what was the economic status of Mexico in the 80s, in 2000s, in 2010? And basically what we do, obviously very important also, human development variables. So for example, the Human Development Index, how was Mexico doing during the 80s, during the 2000s, during 2010? What was the GDP per capita, the GDP of the country, the inequality? If we collect all these data, and this is basically what we have been doing, we are trying to collect this data for the countries that it is available for at a subnational level. And we have been exploring urban clusters, urban cities, rural areas, 40 years of data basically, and more than 20, right now we have like 26 variables that we are exploring. Then we can use data science to do this. And let's say, for example, that we have collected all that information from different parts of the world. And let's say we this time want to say we can find a relationship between the future number of dwellings, or if we can predict the number of dwellings that is in different areas of the world by, taking a look at the different drivers. So geographical drivers, the economic drivers, the human development drivers. And then you can use statistical models to do this. And for example, this is just one of the algorithms which you can do this with, random forest algorithm. And now you can see that the relationship improves a lot. Now, like these type of algorithms are able to come up with better or more robust models to predict the change. For example, in this case, I'm taking a look at whether we can predict the change in the number of dwellings in a subnational region, so in Mexico City, in London City, as well as in rural areas, right? Using all of this information, we've been able to improve the models in order to predict change. We can take a look at, for example, if we can predict the number of dwellings, but we can also take a look at if we can predict how much more construction area will be in a country. So again, selecting one variable and selecting drivers that I suspect that are driving this variable, and then try to see if there's a good correlation between these drivers and the target variable that I'm taking a look at. So for example, this is one model, again, with random forests. You can also use KNN models. You can also use standard statistics for this. And then try to see the correlation there and see if the models are having a good performance. So this is, for example, trying to predict for different regions of the planet, if we can understand what will be the constructed area in those in the total build-up area in those regions. And you can do the same, for example, with the construction volume, because, for example, in many regions, the building height is an important factor. So again, you can build a model with all of these data sets coming together, and then try to come up with better or more robust relationships to do that. So this is one way, we're improving upon this kind of things. And then you may be thinking, well, okay, so you build a model that is able to tell you or predict how much has been observed. So how can you use this to make, for example, a forecast into the future of how many more dwellings we're going to have, how many more residential housing units we're going to have? So just to give you an example of how this can be used, and again, taking a look at Mexico, and this yellow line that you see here is Mexico City. These 1980, 2000, 2010, and 2020 are actually the observed number of dwellings, residential dwellings, that the census information is telling me that we have for Mexico City, okay? So as I was telling you, these are known observations of the variable that I choose, which in this case will be, if I'm trying to predict the number of dwellings, that will be my target variable. And then I can see how my model is performing. So I just choose an initial point for my model, and then I provide for my model all the variables of change that I was mentioning to you. My known observations will basically be how much more people is coming into Mexico City between these decades, how many more buildings, how many more GDP we have in the area, how much more human development we have in the area, and that way we can ask the model to make a forecast of or a prediction of how many more dwellings we're going to have in that area. And I do the same if my starting point is the 80s and I manage to do that for 2000s, then I do the same within this decade with the new variables that I have or with the observed development of the country. And then I try to make that forecast and so on and so on and so on. So the thing is, what you're seeing here is the performance of these kind of models trying to predict what has been already observed. But beyond here, what does the model need? If, for example, I want to make a prediction on how many more residential dwellings we're going to have in Mexico City in 10 years, then I need to provide the variables, how many more people, what will be the human development within the next decade, what will be the GDP within the next decade. So where do you grab that? That doesn't exist, right? We haven't observed that information. So how do you grab scenarios of these variables if this is the future? So basically how we do that is basically using narratives of the future. And this is something that is commonly done in climate science. So the frameworks are already in place to facilitate this integrated analysis of future development. How many more people? How is the economy going to do? How is the human development going to be in the future? This is known as the shared socioeconomic pathways. Maybe some of you have already heard about it, but they're called SSPs. Basically, the SSPs are like different narratives of how we're going to evolve in the future in terms of urbanization, in terms of the economy. And this takes into account different variables. Are we going to have technological advancements? Are we going to build more densifying cities? Are we going to have more kids or less kids? So there are different routes that we can take as we move forward. And I will just focus here on the SSP2. For example, the SSP2, which is this one that you see here. The SSP2 is what they call the middle of the road in climate science. They're saying, well, we continue burning fossil fuels as we do, we continue building as we do, we continue having more or less the same amount of kids that we have. And so we make predictions of the future GDP and the future population of the planet. So if I use those variables to make, for example, input them here and make a forecast of how many more buildings or dwellings we're going to have in the future, then we can do actually a forecast of exposure. So what I want to show you here is just an example of how we can do this, for example, in Southeast Asia. So under the following scenario, on SSP2, we're going to assume that the demographic growth is as historically observed, and the human and economic development in this area is as historically observed under an SSP2 trajectory. And then what I'm showing here is if in the present we have these many buildings, these are residential dwellings distributed in a hexagonal grid in Southeast Asia. This is in 2020. By using the SSP scenarios, then by 2030, we can expect this increase. By 2040, this increase. And by 2050, this increase, okay? So now we're going to track it again, but let's put some numbers there. So right now we see it more or less around 180 million dwellings in Southeast Asia. By 2030, we're going to have almost 30% more of that. By 2040, almost 50% more. And by 2050, almost 70% more. So this is basically how we can use narratives of the future to come up with new predictions or with scenarios of future development of residential construction, for example. So the other question that is important is where, and this is where I'm going to show you this slide again. But why are we concerned about where construction is happening? As I was telling you, we're concerned because if we map this increase in residential construction against, for example, what is the likelihood that we're going to see an earthquake in these regions, then you're going to see in these big spikes of color that you see there is high residential development in areas where seismic hazard is big. What do I mean by seismic hazard? The probability of seeing a damaging earthquake within the next 15 years, okay? So it means that mapping where new development is happening is quite important as well. So how do you do the where? How did Alejandro knew that, for example, Jakarta is increasing more in this hexagon and not in this other hexagon? The way we have been doing that, and I wanted to show you this is important as well, actually. So under an SSP2 scenario, an increase in exposure by 2050 in Southeast Asia means that we're going to have 134 million more people, almost that amount of new residential dwellings and buildings. But the interesting thing here is that you can see that 60%, around 60% of that growth is happening in regions of high seismic hazard. So actually, what you can already see that risk might be increasing here, because if we're expecting this many more people, this many more dwellings in zones of very high seismic hazard, then this means that our condition of risk might increase in the future. And so how are we doing this? How are we deciding, well, in which areas we are going to have more people or allocate more building construction in our models? We do this, there are different ways of doing this. In literature, you might find the most common one is called geographic weighted regression, where basically you explore on a grid how different variables are actually affecting the probability that a land area will be developed. So within those variables, we analyze, for example, in each pixel, what is the town density, what is the proximity of that pixel to towns, to highways, to amenities, and then we use that information again in regression, in classical statistics, to calculate the probability that a given unoccupied area of land will be built up in the future. So we developed this, this is called probability transition matrix. And basically what we're seeing here is for Italy or for Germany, within the next 30 years, where is most likely that we're going to see urban development happen. So these are important rasters or important data sets, because it allows us to place the new development in the regions where we think it is most likely to happen. And that's how we identify, for example, that in Jakarta, in certain parts of the city, we're going to have more development than in others. And you can do this at any resolution that you want. It's basically the amount of variables that you can collect here, what's important, and the resolution of those variables. So what you're seeing here is, for example, a forecast of the future built-up area in the European Union. I think you have seen this before. Maybe Professor Silva was showing it, but this is basically how these data sets are developed. And then I have talked about, so how many more people, where can we locate these people, how many more buildings, where can we locate these buildings, this new construction, where is it going to be located? And I talked about, using data science to do this, machine learning models. So all of this is just going to tell us how many more people, how many more buildings we're going to have. But how vulnerable are they going to be in the future? This is something that I don't think we have enough or robust data yet to come up with statistical models to do this. So basically, what is seismic vulnerability, or what do I mean by seismic vulnerability? So seismic vulnerability is basically the convolution of two things: seismic fragility, which is the likelihood that an element exposed to seismic hazard will suffer damage, and then vulnerability will be the likelihood of that element to suffer loss due to ground shaking. So these relationships are typically presented in this way by a curve in which in the x-axis you have the different levels of intensity, and in the y-axis you have how likely it is that a building will suffer damage due to that. So in the future, the question is, in the future, how is vulnerability or fragility going to change? So we can focus here on two things. I think there are two main concerns here. We can take a look at the existing building stock and how certain effects are going to change its fragility and vulnerability. In the existing building stock, for example, aging effects are important, material degradation, exposure to certain elements can degrade materials, design flaws that within time become more apparent. But there are also environmental factors, damage accumulation. For example, when an earthquake happens, a house gets damaged. but then it's already damaged. So when the next earthquake happens, this building is more likely to fail or to suffer damage due to that ground shaking. Settlements due to bad foundations. This is some environmental factors that can happen. But maybe the most important are the human factors, because we make a lot of adjustments to the current construction. In Latin America, for example, we add new stories to existing buildings. We can also demolish existing buildings and build new ones. So all of these things are going to change the future of fragility and vulnerability of the building stock. And this is on the existing building stock. What about the new buildings that we're going to generate, the new buildings that we're going to build, let's say? So there are two main factors that can influence that: the policies that we have, for example, design regulations, if there are seismic codes in place or not, if governments are willing to retrofit already vulnerable construction. And in implementation, basically, we're going to take a look if having a seismic code is enough. Sometimes we have a seismic code, but people don't follow it due to construction informality. So these are the kind of factors that we can take a look at. So regarding the existing building stock, what I'm saying is this. I think this is a very nice photo from Lalman's thesis, where David Lalman's thesis, where he is basically showing how, and this is in 80, how is we start building a building because we need housing, but then we start adding extra floors because we need more appliances or we need more space, or the family increase, so we add a second floor and then a third floor, and this is how existing construction can become more vulnerable. Basically, because these are non-engineered modifications. So as time passes by, we're making our buildings more fragile. But then also regarding the new building stock, we can take a look at how are we going to build in the future. And here I'm putting this photo as an example. This is a photo that I took in Nepal. This is a region called Bungamati. So in this region, when the Gorkha earthquake in 2015 struck, this is a region that suffered a lot of damage. And you can see some lots are already undergoing new construction, new development. People is already building back their houses. So how are those houses being built? Are they going to follow new regulations? Are they going to follow better construction practices? Or are they going to be built in the same way as before? So that is basically fundamental into understanding whether we're going to have a higher risk in the future or less risk. And these are things that are difficult, very, very difficult to take into account in models. So how can we model this? How can we make models that take into account all of these different effects that I'm talking about here? So rather than coming up with models to predict the future, I think that we can take a look at what climate scientists do, and instead come out with proposed narratives of what we can do in the future. And for example, here, just as an example, I'm proposing two possible narratives for the future. So what if we assume in a narrative one that we're going to proceed building as usual? So business as usual means we're using the current codes, the current seismic provisions. We have the same level of informality in construction. So if, for example, if Indonesia, only 30% of the people is following the code, then we keep with that trend. Whereas we can have a different future, or a future B, that I call safer standards. And in this future B, we're going to have more modern building codes, safer standards available for people. And then people is more likely to add to this or adhere to this new building construction criteria. So let's say that we have two possible narratives of the future that I'm just proposing here, but you can propose a future C, a future D, a future F, as you wish. But just to show you, for example, if we implement two possible futures for the Indonesia, the Southeast Asia scenarios that I was showing you before, on the future A, where we're going to have, almost 200 more million people in the region, but building as usual, then by 2050, 93% of the people are still going to live in dwellings that have insufficient seismic provisions. Whereas if we proceed on a future B or on a path B, on a proposed narrative B, where standards, new building standards or safer standards, better building codes are widely adopted by 2050, then the number of people that is going to live in dwellings with insufficient seismic provisions is going to be dramatically reduced. And this is going to translate effectively into lower risk. So I think this is the way in which we can move forward regarding how vulnerable the new building stock, the new built environment is going to be in the future. I think we can propose these narratives. I think this can be things that as nations we can aim to or try to adhere to in the future. And then following these rules, following these proposed targets, we might be able to reduce risk. So I'm just going to finish with how all of this comes together. So for example, how does all of this come together? So Alejandro was telling me about, how to account for new people, new construction, gathering all these variables, proposing different narratives of vulnerability. So with current models, we are basically able to understand what is our current condition of risk, let's say. Then because we have time-dependent exposure and time-dependent vulnerability, then we can understand what is our current trajectory of risk. And then that means that if we propose, as I was telling you, different narratives of how we can reduce it, more people following the code, more people building better, or retrofitting more structures, then we can select some targets and try to see which measure of mitigation is more effective than the other. So this is quite important. Why? Because I think we all know that building safer buildings is always going to reduce our risk. But with this kind of analysis or assessment, we can estimate by how much, okay? So I think this is important for decision makers. It's important for decision makers to be able to tell them, we need to adopt a new building code, for example, but also adding that statement with, by doing that, we might be saving $300 million every year, $500 million every year, because we're reducing our condition of risk. We're reducing the expected losses that we can see from earthquakes in the future. And so we have done this actually in several studies. I'm just showing you here as an example, the Dominican Republic. We basically try to understand what is the change in risk at a subnational level in the Dominican Republic. And I'm just showing you here, we can focus on two examples. The yellow area, this area right here, is the trajectory of risk of the capital of the country called Santo Domingo. And this pink area right here is the risk trajectory of a north city in the country that is developing quite fast. It's called Santiago de los Caballeros. So what is happening here? In Santiago de los Caballeros, in the north, because the city is developing, it's attracting a lot of people from agriculture into services. A lot of people is building their new houses there. And because this city is basically located in very close to this fault that you see here, which is actually responsible for many earthquakes in the country's past, the condition of risk is actually increasing. And you can see that we have calculated a main line trajectory of risk, but also within the shaded area, you can see the different narratives. In some narratives, risk is increasing even more. In some, not so much, but you can see the main risk is increasing there. The main narrative is increasing there. And then we can explore how we can reduce earthquake risk here. Then we have the capital, and if you can see in the capital, risk is not increasing so much. In fact, it's slightly decreasing. Why? Because the capital is already mostly built up. Adding more construction in the capital means that we are going to remove all construction and build new construction that is probably going to adhere to the new code in the country. So it is most likely that risk here will actually decrease. So it's actually quite interesting to see that we can do these kind of assessments. And then we can also support decision makers in each municipality by, for example, trying to understand how to reduce risk in the north of the country and how to reduce risk in the south of the country. We did this basically by analyzing what's better. If adopting new code, it's going to be more effective than, for example, retrofitting already vulnerable structures. And the main conclusion that we found here is that in the north of the country, due to the rate of the development, the most effective risk mitigation strategy is just adopting the code from now on, making sure that everyone's building safer houses. Whereas in the south of the country, what was most effective is just building, trying to retrofit the already vulnerable constructions, because the new buildings are going to follow the code most likely. This is a heavily controlled area. There's a lot of urban planning because it's the capital. So the most effective mitigation measure there will be to start retrofitting the already vulnerable building stock. So this is how actually risk forecast can be useful for decision makers. So I'm just going to end up here because I think this is a lot of information. So I'm just summarizing here points that I think it's important for you to remember. The first one is that the built environment is evolving in response to many factors, not just we need more houses or the economy is doing great. There are many things in play. Urbanization, the average people per house in the Dominican Republic, buildings house 4 or 5 people, whereas in Albania and Serbia, it's much less than that. So all of these factors come into account when we are trying to estimate the future number of buildings, houses that we are going to have in the future. We can also simulate scenarios of exposure and vulnerability and explicitly accounting for uncertainties associated to these processes. For example, are we going to have more kids? Are we going to have less kids? Are we going to build better? Are we going to build maybe not so bad, not much better than what we're doing now? So I was just giving you examples of how this can be explicitly modeled, and then we can get analysis of the impact of that in the risk assessment. Future risk can help identify and mitigate drivers of risk before that risk becomes our present reality. So basically, we're trying to do this in order to understand what will be the risk in the future and try to mitigate it. We all know that building better and more sustainable will lead to a safer future, but through the study of future risk, we can help quantify how much is that, and then help the decision makers make better informed decisions. And this is fundamental not just for earthquakes, but also for other natural disasters. So I think most of what I've talked about here is relevant to earthquakes, but also to floods, to tsunamis, to earthquakes, to hurricanes, to all kinds of natural hazards. So I think this is important in general for natural disasters and trying to reach a more resilient world in the future. And this is it. This is basically the end. Again, because this is a lot of information, I am just giving you my contact here. If you have any questions, I'm happy to answer them now. Or if you have questions in the future, this is something that you would like to look into the future, you can have my contact and then just reach out to me whenever you need it. So thank you very much for the time. And that's it. This is the end of my presentation.
Thanks a lot, Alejandro. Very nice to see the whole chain, from, the data up to the estimation and, forecast or prediction of future losses and risk. So are there any questions before Laura? No, we're just clapping.
Okay, it's a lot of information.
I was just clapping because it was a super interesting presentation. And if I can break the ice, I just would like to know if you are planning some exercise, for example, for estimating the impact of financial support for retrofitting, like the ones that have been introduced in Italy, for example, because government complained that there were a lot of money, let's say, spent in supporting renovation of houses, but they do not have a clear idea of the benefit that this money can cause in the future. So it will be really interesting to demonstrate the ratio of investment versus benefit.
Yeah, that's a very good question. Actually, we are doing this. We are doing this in Nepal right now. So, for example, in Nepal, in 2015, they had a big earthquake. And this earthquake destroyed a lot of houses. And the Nepalese, they decided that from 2015 on, they are going to rebuild these houses. This is almost 1 million houses. So it's a lot of houses. but they decided that they're going to build them with following new seismic criteria. So let's say much better buildings. So basically what we're doing now is we're using these forecasting techniques to set the point of two possible futures. When the Nepalese decided to build better, that's going to be one risk trajectory. And when if the Nepalese didn't decide to build better, just, the earthquake happens and we're just going to rebuild as we go along. And so basically what we're doing is doing the analysis of how much the country has saved by simply adopting from 2015 on that new regulations, and by introducing almost a new 1 million new structures that are more resilient to earthquakes. And we don't have the final numbers yet, but the nice thing to see is to see the government officials being happy to see the savings that they're having, because this is allowing them to ask for the government to keep funding this kind of activities and to give them credibility to the public. So basically showing to people that this is actually saving lives. So we are doing this from the economic perspective, and we're also doing this from the fatalities perspective. So in both calculations, it's quite clear. I cannot tell you the numbers now because we're still like deciding how are we going to assign certain vulnerability functions and things like this. But preliminarily speaking, there is a massive decrease in risk due to simply deciding to build 1 million structures better from now on. And from 2015 to 2025, all the new structures that they have added, following new code regulations, it's a massive amount of lives that are being saved. And we're being able to account for that and showing that in risk profiles to the government officials. So they're very happy with this. Hopefully you will see this as a publication in the future, but also hopefully you will see it in maybe in the World Conference that we're going to have right now. So we're still doing those final calculations, but it's quite interesting to see that this is helping give credibility to these kind of decisions. And just to end up saying that we're also trying to do this at a global scale. So as you know, the Global Earthquake Model Foundation has a risk model for every country in the world. We're forecasting exposure, proposing narratives of vulnerability for all the countries, and we are hoping to have also gross numbers of how much we can save, choosing, let's say, business as usual or a better future in construction. So this is something that we also want to do at a global scale. But thank you very much for the question, Laura. I think it was very good. I hope I answered a little bit on how.
Sure. Thank you very much.
Are there any other questions? Students?
Alexander, I think he has. Yes.
Oh, yeah.
Yeah, so you mentioned in one of the future scenarios a change in how much building regulations are actually followed. So I was wondering, how do you even know how well these regulations are followed? Because I assume that after an earthquake, there might come out, oh, there was these didn't follow regulations, otherwise they would have not collapsed, and maybe corruption scandal comes to life. But these things usually happen way after the fact. So how do you quantify that? Yeah,
so this is challenging to do, and imagine that we are doing this for every country. So how do you do that for every country? So there are some techniques that we use as modelers. The first technique that we use to try to understand if construction regulations are being followed or they are feasible for the population of the country is taking a look at informal construction in the country. Why do I mean by informality? For example, the census of every country is able to tell you how many people have in their residential dwellings, their floor is made of dirt, for example. By trying to understand how many people live in that kind of condition, then you can more or less understand how, like, these people certainly didn't hire an engineer to build their houses, because if their floor is made of dirt, or for example, they don't have accessibility to water, to potable water, then it means that most likely their dwellings are not prepared for building for earthquakes. So we try to estimate informality in this way. This is one proxy way of doing it, but it's still not enough, because, for example, very good income families might also choose not to hire an engineer. This also happens. So how do you do there? In every country, we try to liaise and collaborate with professionals and local experts in construction, and they more or less allows to understand, yeah, middle income families in this country, they tend to follow the code, some don't follow the code. So we try to understand that in rough percentages, and then those percentages become the informality of the country. So this is basically a parameter in the model. And this is very common. This is mostly the way we do this because this is very difficult to capture, right? But we use this kind of proxies to do that.
Okay, thank you.
So
Yeah.
you have some like local experts somewhat.
Local experts, exactly. They are.
So I was wondering because I mean your type of studies is very you know, data involved, like very much. I mean, to collect and gather this data, I mean basically I was wondering how you can basically do this on a nation basis for all nations on Earth.
Yeah. Yeah, at a global scale in the GEM Foundation, well, it took us almost 10 years to come up with the global exposure model. Why? Because all of these nuances have to be taken into account if you want to do reliable models. Remember that at the end, the models have to be validated and they have to give reliable metrics. So we always validate our models, for example, by modeling events from the past. For example, the 2015 Gorka earthquake, the Turkish earthquake that just happened. If we model that earthquake, we have to make sure that our models are giving us the observed level of damage, the observed level of losses. And this is how we make sure that our models can be validated and they are reliable. So this is a massive effort, actually. And this is why it has taken 10 years, 15 years to do this. And this is why updating those models is also like a massive undertake. But so at the GEM Foundation, we rely on professionals, but also local collaborators to do this in a good way.
Yeah. Another question. Sorry, and we can let students ask more questions. But so I guess the insurance companies, I mean, are also like doing the same type of estimations. So I mean, do you work with them? Do you collaborate, or is that like competition? And how does that work?
That's a very good question. So actually, GEM, the Global Earthquake Model Foundation, is a nonprofit organization, and we're mostly funded by private and public institutions. So public governments, for example, the Italian Civil Protection, the government of Taiwan, Canada, etc. But also we work closely with private sponsors, which are insurance and reinsurance companies. So what they have, this partnership, what it's doing is basically they are relying on us in many ways to calculate and estimate the risk. So they know and understand if they are able to enter these markets, if it's feasible to enter, what are the kind of premiums that need to be charged. They always compare our models with their own models to make sure that that they have two vision of risk, two hypotheses of risk, and being able to provide these services safely. So rather than being competition for the insurance market, we're actually a supporting or a technical partner to them. And this is one of the main uses that the risk models have. For example, in Nepal, again, in Nepal, they are using the national model to try to come up with a premium for earthquakes. And this is why these models are super important. They give you a picture of risk. You come up with the appropriate premium for earthquake risk that the standard family should pay, and then you try to see if the families can pay it, if you fund it through taxpayer money, or if you fund it through private means, basically taking this risk, putting in a stock, and then see if private individuals want to take this risk and profit from this, or assume this risk. So this is actually all these kind of different tools to transfer the risk that we have to private individuals. The main tool to do that is this kind of model. So we actually do rely on and liaise a lot with insurance companies to do this.
Thanks.
Yeah.
Good. Are there any questions, guys? Not for the time being.
Okay. So thank you very much for your patience. I think it's a lot of information. It's always and it was a long presentation, but thank you very much for the attention. And again, like I remain attentive if there's anything you would like to learn in the future or anything I can help with. It will be a pleasure.
Thanks a lot, Alejandro, for your very lively presentation. Very interesting.
Thank you.
Okay, just a last word, guys. It's very likely that presentation in 2 weeks' time will be cancelled because it was supposed to be given by Julio and Ilona, if I'm correct. And Julio told me that he's just overload with work at the moment. So, well, it's still on the program, but it might be cancelled. Just to let you know, I will let you know as soon as I know. Okay, thanks a lot in any case, and see you soon.
Thank you. Have a great day.
All right, bye-bye.
Thank you. Bye-bye.
Thank you.